All right, so now we're going to look at defining a definition of something called a critical point. And this will be something that turns up frequently on in the class and in coming chapters and on the AP test. We say a number C in the domain of F is called a critical point if either f prime of the C value is 0 or f prime of C does not exist. So critical point, we're basically looking where's the first derivative 0 or where does the first derivative not exist. So we'll do an example or two with that and then go on from there. So for this example, we want to find the critical points of the function f of x equals x cubed minus 9x squared plus 24x minus 10. So what we're going to do is find the critical points. We need to figure out what's the first derivative and then find where is it 0 or where does it not exist. So the first derivative in this case would be 3x squared minus, that would be 18x plus 24. This is just a parabola because it's ax squared plus bx minus c, or ax squared plus bx plus c form. This is a parabola, so it will have no parts where it doesn't exist. There's like no division by 0 or square roots of negatives or any of that weird stuff that can happen here. That's just a regular old parabola. So we're going to be interested in where is the parabola equal to 0. That's how we're going to find our critical number or critical points on this. There is no point where this is undefined, so we're not really worried about f prime of c does not exist. We're not worrying about that part so much because that's not going to happen since our first derivative has this form. We're going to just focus on where's the first derivative 0. So get 0 equals that. I'm going to try to factor this. So I'm going to factor out a 3 first. And we'll get x squared minus 6x plus 8. That'll factor as x minus 4 times x should be minus 2. And then we could set the x minus 4 equal to 0. Solve it for x and get x equals 4. And we could set the x minus 2 equal to 0. Solve it for x and get x equals 2. So these are my two critical points. These two values here. They are inputs. They are x values for which the first derivative is 0. And due to the form of our first derivative just being a parabola, we didn't have any inputs that would make the first derivative undefined. So we're done. These are the critical points for that particular function that we started from here. That's its first derivative. Setting it to 0 got us our critical points. For the second example, we want to find the critical points of the function y equals absolute value of x. Now, one thing I want you to remember, this is, the shape of this is just a V shape. This is what absolute values graph looks like. We have what's called a cusp here derivative of all the tangent lines on this part of the line is -1. The derivative of all the tangent lines on this part of the line is +1. And since it abruptly changes due to the cusp there, the function is not derivable. There has no derivative. There's no derivative at x equals 0, the point of that. Like if there's a smooth transition from one to the other, then it is differentiable the whole way. But if you have any of these where it like comes down and makes a sharp cusp, you won't be differentiable there because the derivative abruptly changes from, or the difference quotient leads to one number on one side and the other number on the other. If we looked at the graph of its derivative, its graph is it's 1 when you're on this part of the line segment here, and you're at -1 when you're on this part of the segment, because all the tangent lines on this segment, the left-hand segment, all those tangent lines are negative. All the tangent lines on the right-hand segment here are positive. So you end up with this for your derivative. So this function, the first derivative, it's either it's -1 or it's +1, or it doesn't exist here at 0. So where that cusp is, that is our critical point. So y prime does not exist at x equals 0. So x equals 0 is the critical point of y equals absolute value of x. So that's an example of where the first derivative does not exist. And in this case, it was kind of due to a cusp, which is an abrupt change from one form of a function to another. You'll see this a lot from piecewise defined functions also, where the function abruptly changes form from one to another, and that creates a sharp angle called a cusp. Okay. So, stop there.